Good morning, good afternoon, everyone. Thank you for joining our Cognitive Systems Institute Group Speaker Series call. I hope everyone can hear me. If you do have trouble hearing, type something in the chat. Turn your speaker up as loudly as you can. And I'm excited to introduce our presenter today, Pat Langley. He serves as Professor of Computer Science at the University of Auckland and as the Director of the Institute for the Study of Learning and Expertise. He has contributed to artificial intelligence and cognitive science for 30 years. He was founding executive editor of Learning, and he's currently editor for Advances in Cognitive Systems. His current research focuses on induction of explanatory scientific models and on architecture of intelligent agents. So let me turn the call over to Pat, and thanks for being our presenter.
Thank you, Diane. Okay, I assume that you can hear me okay. Yes. Thank you for everyone for coming. All right, so here we go. So today I'm going to give an overview of the cognitive systems movement, in particular work on interactive cognitive systems. I'm not going to spend a lot of time talking about my own work. I'll only mention some in passing. Let me start by telling you about the cognitive systems paradigm and why it's a movement these days. So if you go back to 1956, and at the Dartmouth meeting that launched the field of artificial intelligence, there were really two broad kinds of aims for the field. The first was to understand the mind in computational terms, and also to actually build computational artifacts that reproduced all the mental abilities that we find in people. Now, if you look at the history of AI, I think it's fair to say that that view, that agenda, continued through the mid-'80s. But in the past 20 years, even 25, 30 years, there's been the adoption of some very different goals. And now most AI researchers are happy to work on simpler, more narrowly defined problems that I will argue don't really involve much intelligence. Again, going back to the origins of AI, in the 1950s and 1960s saw a number of key insights and breakthroughs that underlay a lot of early advances in AI, but also cognitive psychology. The first was the rejection of the behaviorist's position that we should be focusing on simple tasks and on learning from those tasks. That's on the one hand. The other was that there was a big push in the 50s for using information theory to understand cognition, and very much focused on statistics. So the cognitive revolution really rejected both of those, and instead redirected attention on tasks like problem solving, language understanding, other things that involve thinking. And just to be clear here, the word cognition doesn't mean psychological. That seems to be a confound people have. Cognition means having to do with thought. And cognitive psychology is a branch of psychology that studies that. And AI was centrally concerned with cognition. The other shift was a focus on mental structures that supported such cognition. So issues of representation became central to AI. And yet, what we find now is many modern AI researchers seem to have abandoned these key insights. And so you might ask, well, why has that happened? Why have people retreated from these original insights and the original aspirations? There's a number of reasons. I think one of the most compelling, understandable, is there's been many commercial successes of what you might call niche AI, where people have built very narrow systems that focus on very specific problems, and they've been commercially wildly successful. Data mining is an example of this, where you build a classifier from training data, and it's very, very good at predicting where to place ads or whether to accept credit cards. But we've also seen much faster processors and much larger memories. And what that has done is let people get away with using really simplistic, sometimes blind search techniques, and with using statistical schemes rather than the deeper kind of reasoning that traditional AI explored. And so it's been easy to get away with that because of the faster processors and larger memories. There's also been a shift in the field toward a focus on quantitative metrics. And that's partly been encouraged by funding agencies, but also, but sometimes it's been grassroots. In machine learning, I actually helped get people concerned about that back in the 80s and 90s. But the problem is that it has too often ended up encouraging people to do mindless bake-offs, where they show they're a little better than someone else, but they don't understand why. And finally, there's been formless trends that have been imported from mainstream computer science that have favored approaches that were simple enough, that simple tasks and simple techniques for which you could prove optimality, independent of their practicality. There's a concern with sort of formal results that something's optimal, for example, in the limit. And again, I think that these is very much different from the original tradition of AI and has taken people away from the original vision. The catch is that many of the original challenges that were set back in the 50s and 60s are still there. And there's plenty of opportunities for research. But unfortunately, the word AI has now acquired such limited connotation that we need a new label. So we want some term that refers to the discipline that designs and constructs and studies computational artifacts that really explore the full range of intelligence we find in humans. And so I'm going to call that, and have been calling that, cognitive systems. It's not my term. It's a term that Brockman and Lemnios invented for the Cognitive Systems Initiative that they launched at DARPA back over 10 years ago. And many people who are working in this area refer to what they're doing as cognitive systems. So I think I'm on safe ground here. Now, in the next part of the talk, I'm going to go over 6 characteristics that distinguish cognitive systems research from what has become mainstream AI work. If you want to see more details of that, I have an essay on this in the journal Cognitive Systems at this URL, and I've got that in the references too. The first is a focus on high-level cognition. So I think it's clear that people share many abilities with dogs and cats, things like the ability to categorize objects or to learn statistically from experience. But only humans can understand language. Only humans can generate it. Only people can solve novel and complex problems and build complex plans. Only humans can design and use complex artifacts. I know that animals can do very simple versions of some of these, but not at the level of complexity that people have. Only humans can deeply reason about others' mental states or think about their own thinking through processes of metacognition. And so reproducing these abilities computationally is certainly one of the key challenges in cognitive systems work. Another feature is the reliance on structured representation and knowledge. So another of the key insights behind the AI revolution in the 50s was that computers are not just number crunchers. They are general symbol manipulators. They can encode content as list structures, including logic, not just logic, graph structures, similar formalisms. They can create, modify, and interpret that content. And they can use numbers, but those numbers are primarily annotations on the symbolic structures. They're not primary. So this paradigm, the paradigm of cognitive systems, assumes that representing and reasoning over such rich symbolic structures is key is necessary for human-level cognition. A third point is that cognitive systems takes, well, a systems perspective. Most AI work these days focuses on components. If you ask someone whether AI is about algorithms or systems, most of them will tell you it's about algorithms. But that's not enough. If you're going to ever build something that's larger scale than a standalone single application, something that really has the breadth of human and scope of human intelligence, you need to talk about how different abilities fit together, how they interact. You need to build integrated intelligent agents that combine those abilities, and maybe even want to develop theories, unified theories of the mind, as is proposed in some cognitive architectures. I think that if you don't do that, you're going to be limited to what you might call idiot savants, systems that are really good at one thing, but not having a whole diversity of abilities like you find in humans. Fourth, work on cognitive systems also draws inspiration, at least, and ideas from findings about human cognition. How they, and this was true in early AI, and it's true in the cognitive systems movement. How do people represent knowledge, goals, and beliefs? How do they use their knowledge? How do they acquire that knowledge from experience? We still have lots to learn, lots to gain from that strategy. And even if the system you're building does not work exactly the way that a person does, well, that's okay. You can still look at human abilities and use them to drive research because they pose challenges. There are things that people can do that our system still cannot do, and we can use them as role models. Fifth is reliance on heuristic methods. This was an early distinction between AI and mainstream computer science. Heuristic methods are not guaranteed to find the best solution. They aren't guaranteed always to find any solution. But in practice, they can greatly reduce search. They can make problem solving tractable, and they can apply to they let you tackle a broader range of tasks than if you limit yourself to methods that have formal guarantees. They mimic what we see in humans, in that this is what Simon calls satisficing. That's finding an acceptable solution rather than finding an optimal solution. And finally, cognitive systems has a more Catholic view on evaluation. Yes, you can run experiments to show that you're better than some earlier method, but that's not the only game in town. You can also demonstrate entirely new functionality. You can introduce novel approaches to well-established problems. You don't have to have running programs. You can do analyses of challenging tasks, or you can have architectures or frameworks for integration. So together, these encourage kind of exploratory research. And I think that's really important because we really do not understand very much about the mind yet, despite what some people may claim. And now, studies are still going to need to take positions, make claims about things. We need to support them, but there's many different kinds of evidence. It's not just proofs, and it's not just experiments that show you're better than the current state of the art. Sometimes there is no state of the art. Now, let me just pose three hypotheses for cognitive systems. The first two I've taken from Al Noel and Herb Simon's 1976 paper that they wrote for their Turing Award. You've probably heard of these. The first one says that the ability to encode, manipulate, and interpret symbol structures is necessary and sufficient for general intelligent action. They call this the physical symbol system hypothesis. The second is that problem solving, and what they mean by that, tackling new problems you haven't seen before, involves heuristic search through a space of states, which are themselves described as symbol structures generated by mental operators, which are other symbol structures. Now, these have been around for a long time, and I don't think they're even controversial in mainstream AI, but there's more. I mean, these definitely are central to cognitive systems and relate to some of the features I mentioned earlier. But there's a third that I call the social cognition hypothesis. And it says that intelligence, at least the kind we find in humans, requires the ability to represent, reason over, and use models of other agents' mental states. That is, a lot of intelligence is about interaction with others, with other agents. And many of our key abilities involve thinking about others. So that's the overview of cognitive systems. Let me just shift and just give you a few examples of interactive cognitive systems, systems that engage in this, that demonstrate this, all three of these hypotheses, but with an emphasis on the third one. The first is a tutor for algebra that came out of Carnegie Mellon. It's offered by a company called Carnegie Learning, and it helps students improve their ability to solve algebra problems. And it has a lot of knowledge about algebra in terms of condition action rules. It infers models of students' knowledge from their interaction, and it will, as a result, provide personalized instruction. Here's the interface here. I won't go over it. But it's been adopted by hundreds of U.S. middle schools, and studies have shown it improves student learning by 75%. This was developed quite a while ago. Here's another older system. TAC Air SOAR was developed using the SOAR cognitive architecture that reproduces pilot behavior in tactical air combat. It combines abilities for spatial temporal reasoning, for plan recognition and generation, for simple constrained language use, and coordination with other pilots. It flew 722 different missions during a simulated training exercise in '97, and has led to a lot of interest, a lot of follow-on work funded by the U.S. military to develop more systems like this. Then there's Facade, somewhat more recent. This is an interactive drama system where you enter a graphical environment where there are characters who interact with you, the user, through text, and with each other. They understand in a very fairly shallow way what you're talking about, and they generate responses. They control their gaze and expression. They definitely have distinct personalities, and they do have a rich knowledge base that lets them make inferences about what's going on, carry out physical activities, and engage socially. And if you haven't tried this, look it up on the web. It's very interesting to interact with and fun too. There are other examples. Again, going back to the 90s, the system Trains, which was a conversational aid to help users create plans through spoken dialogue. Collagen, which was not spoken language, but did help users interact, help users operate complex devices. Tutorial dialogue systems, a number of these have been developed that converse with students in spoken language and give personalized instruction. The Virtual Human Project at the Center for Creative Technology at USC, and the Artificial Receptionist at Microsoft, both are interactive systems that combine a lot of features and interact with users in spoken dialogue. Let me mention my own work, some of my own work with Alfredo Gabaldon and Ben Meadows recently. We, a few years ago, developed a system called, an architecture called DIGA. It was for conversational agents, and some of its interesting features were that it cleanly separated knowledge about the domain, so what you were talking about, from knowledge about dialogue itself. It also distinguished between conceptual knowledge you use for inference and skills that you use to achieve your goals. It operated in discrete cycles, similar to what you find in production system frameworks like SOAR and ACT. On each cycle, it would observe a new speech act, and we weren't actually doing speech, and we actually weren't even doing sentence processing. But it did take into its input the content the user was trying to communicate. It then would do inferences not only about the environment, but also about the user's mental state. And then it would execute skills to produce utterances based on that state. Here's a sample dialogue. Let's just go through this to give you a feel for it. And again, it didn't actually do the sentence level processing. There's been plenty of work on this. We were focusing on higher levels of dialogue. So this is a case where there's a human medic who doesn't actually know much about medicine, which is pretty common on battlefields, and a computational advisor. That's our system. So the medic says, we have a man injured. The system says, what kind of injury? He's bleeding. How bad is it? Pretty bad. I think it's the artery. Where is the injury? The left leg. And the advisor says, apply pressure on the leg's pressure point. Okay. Has the bleeding stopped? No. Apply a tourniquet, and so on. Eventually, so you can tell that this is an example of joint activity where the two users, the human and the system, are sharing goals to try and help the patient. And what's most interesting about this, and I can't go into the details, is that the DIGA system is incrementally updating its models of the medic's beliefs and the medic's goals, because some of them are getting introduced during the course of the conversation, and it then uses that to generate its utterances. I've got references at the end if you want to know more about this. Okay, so let me just pose some research challenges that might get you, that I think could push the field in interesting directions. New problems can foster progress in any area. And I think that if you think about what kinds of features you want for challenge problems in interactive cognitive systems, it's all the things I listed before. You want to pick tasks that involve high-level cognition, that would benefit from structured representations, that involve system-level integration, that have human role models, that would benefit from heuristic approaches, and I think that depends centrally on processing, on doing social kinds of reasoning. I also think that we need to move beyond the Turing test. It was sort of inspired at the time, but the problem with the Turing test, although it is about interaction, is that it's too undirected. It's not goal-oriented. And most of our conversations, most of our interaction with other agents is about achieving goals. Here's one. I think you'd all agree that spoken language dialogue is a very natural way to provide aid on tasks like driving, cooking, shopping. And Siri and systems like Siri are trying to get at that, but compared to humans, they're very primitive. And what we really need are more effective conversational assistants that will carry out extended dialogue, not just single give and takes, about goal-directed activities, that they will take into account the surrounding task context, that they will infer what Clark calls common ground about joint beliefs and goals, and they can store and use previous interactions with users. So to do this, I think you need to do deep language processing, not the kind of shallow stuff you see in chatbots, reason about others' mental states, and you definitely need to think about social cognition. Another obvious class of challenge problems involves building richer non-player game characters for computer games. There's lots of automated agents in computer games these days. They tend to be really shallow. What we want are more compelling characters that infer other players, human players' goals, use them to their own ends, that will interact with humans in constrained language, cooperate on extended tasks, and even form long-term relationships. Again, I think that to do this, you're going to have to reason about others' mental. Here's a third one. It's a little different. I don't know if you've come across Michael Genesrith. Stanford has a competition every year on general game playing where systems compete, and they have to play games they've never seen before. They're given the rules in a logical language. So this is similar to that, except rather than just playing, people can have lots of knowledge about games, lots of abilities about games. So we want multifunctional systems with the same versatility. So imagine a system that is given knowledge about a new game, and it can not only play that game, as in the general game playing competition, but it can discuss the games with other players. It can provide commentary on games played by others. It can analyze particular game situations. It can even teach a game to a human novice. That's the kind of multifunctional capability you find in humans. And one nice thing about this is it would let you demonstrate the breadth of ability, but avoid the knowledge acquisition bottleneck, okay, because you're given the system knowledge about the game. And usually that's not that complicated. What's interesting is how many things you can do with that knowledge. And this is probably the most controversial and probably the least, and some people will like this, some people will hate this. If you look at how we spend our time as a society, we spend a lot more attention on movie stars than on scientists or scholars. So imagine building a synthetic character actor that has general acting skills, and it can read scripts and background stories for different parts. It can adopt the beliefs, goals, emotions, and personality needed for the role, and they can audition for that part. Most of the scenes would involve interaction with their actors, so they would need social cognition. And the great thing about this is because it's about character actors, you would have to be able to take on radically different characters, and that's a natural test of generality. So I don't know if this would have any near-term business applications, possibly. Certainly many of the extras in movies these days are computer-generated, so maybe we want to have some good character actors too. Now, to do all this, you obviously need integration, but we also need work on the core abilities for social cognition, including how to represent others' mental states, how to reason about them, how to do social plan understanding, and that is figuring out what people are doing from their behavior, but also how to do plan generation to manipulate them, even sometimes maybe by telling them falsehoods, to incorporate that into dialogue systems, and we really do need deeper cognitive accounts of emotions, morals, and personality. So I think we need research on each of those topics, but also how they fit together. So just to summarize, in this talk, I discussed the cognitive systems paradigm, a movement that pursues the original vision for AI as I understand it. I stated 6 distinctive features for work in the area. I posed 3 hypotheses about intelligent behavior, including what I call the social cognition hypothesis. I gave some examples of interactive cognitive systems, and I posed 4 high-level challenge tasks for work in the area that I think could get people excited. So thanks. I think that this is an exciting area. I think that it still has the audacity of early AI work, and it has promises to keep us busy for a long time. All right, I'm done. Thanks. Oh, here's some readings if you want more.
Thank you so much, Pat. This is Diane. Listeners, please unmute your lines to ask Pat a question.
Hi, Pat. While some of the others are coming off mute, I just want to say, as a follow-up question, you don't have to give a short answer right now. I'd love to ask you the question, if you had $100 million to invest in startups that would be in this cognitive systems area, I know you outlined a research agenda, but I'd also like to see what kind of startups and how you might evaluate startups for investing a $100 million investment fund in this area.
Well, sure. I would definitely do something in conversational interfaces, deep conversational assistance. That's the obvious area, and the question is how narrowly to scope that, and how much of the money to use for that versus some of the other areas. But yes, I think it's a great question, and if you have $100 million, please let me know.
We'll work on it together.
Are there other questions for Pat? You'll have to press the unmute on the computer or on your telephone. Well, we are about out of time, so let me just suggest that we continue the conversation with Pat on our LinkedIn discussion group. I'll post something about this. And Pat, your talk was excellent. I appreciate so much you sharing your expertise with this forum.
Thank you.
Pat.
Happy to contribute.
Thanks, everyone, for joining, and we'll see you next time.
Thanks, Diane.
Okay.
Oh, good.
That was awesome.